Okay, today we're going to talk about continuity, and this word you've probably heard before in mathematics, and essentially it talks about the idea that a function is connected when you draw it. We often say a function is continuous if you can draw it without taking your pencil off the page. But we really need a more precise definition of what that means. So continuity has three parts to its definition. And what we're going to do is we're going to look at the meaning of a function being connected at a given point, x equals a, which I'll place here. Alright, so for a function to be continuous at a given point, x equals a, the following conditions must hold. To begin with, there must actually be a point at x equals a. So I'm just going to randomly place a point. Okay, there's my f of a existing. An x value has a corresponding y value, f of a. Second of all, second condition is that the limit as x approaches a of the function must exist, which essentially means that there must be graph around that point. So let me draw a situation where I have the limit existing, and I'm going to just do it here. Basically, we know that for a limit to exist, the function must approach the same value from both sides. Alright, so I have a function, or have a limit existing at x equals a. But you'll notice that the function is not connected, so it's not yet continuous. I've got the first two conditions satisfied, but the third thing that has to happen is that the limit and the f of a value must be the same. So this point right here must actually be placed or equal the limit at that point. And if that happens, then we can say the function is continuous at this point, because not only does the limit exist, but so does the point. Alright? And I've now moved my f of a up to here, so let's just move that. We now have a function continuous at x equals a. Okay, so let's look at an example of deciding whether a function is continuous or not. I have before me a piecewise function, so I'm going to do just a little sketch of that. We have a parabola happening when x is less than 0. Looks something like that. At x equals 0, this point is not included, so I'm making that an open circle. When x is 0, the y value is 2, so that's this point on the graph. And after that, the other piece of this function is linear, which is saying that the y-intercept is 3 and the slope is 1, so my line would start here and move up this way. Alright, so intuitively we could ask ourselves, is that function continuous at x equals 0? And it's pretty obvious that it's not, because to draw this function I would have to lift my pencil off the page. But let's apply the definition of continuity that we just discussed. Alright, so again, to be continuous, three conditions must exist. We're testing x equals 0. So first condition is, does f of 0 exist? So when x is 0, y is 2, it's telling us. So yes, that exists. Condition 1 is met. Condition 2 says that the limit as x approaches 0 of f of x must exist. Well, since this is a piecewise function, we're going to have, and for a limit to exist, the limit must exist from both sides. We're going to have to look separately at the two sides because different equations are involved. So when we're less than 0, we're dealing with this function, and coming from the right side, we're dealing with this function. Alright, so we have to evaluate these two limits. As x approaches 0, if we make x close to 0, this approaches 3. If x approaches 0 here, this approaches 3. And since my two one-sided limits are the same, that means that the limit overall is 3. And so condition 2, which asked, does the limit exist? The answer to that question is yes, the limit exists. Alright, so condition 3 is that f of 0 must equal the limit. And we can see that that is not the case. So for condition 3, f of 0 does not equal the limit as x approaches 0 of f of x. Therefore, make your conclusion, f is not continuous at x equals 0. As soon as we see that one of the conditions is not met, we can say that at that given point the function is not continuous. Okay, there are a number of definitions and useful theorems related to continuity that I'm just going to quickly go through so that you can refer to these as you work through problems involving continuity. The first one is the definition of a function being continuous on a closed interval. And a closed interval, remember, means that we are dealing with the endpoints, including the endpoints. These points are included in the function. The square brackets mean we're including x equals a and x equals b in our function. So often we're going to want to refer to a function being continuous on a closed interval. What exactly does that mean? Okay, so again it means three things. First of all, at every point in between must be the function must be continuous at that point, which refers to the definition we just talked about a few minutes ago. At every point, the three conditions mentioned before must hold. So if I take a point in here, not only must the point exist, but the limit from both sides must exist. Alright, so I'm sure you're wondering about the left and the right side, because how can a function be continuous at x equals a when the function is only starting or being looked at from x equals a to x equals b inclusive? So we have a special way to handle that, and we say that we have defined a function to be continuous on a closed interval if at x equals a the point exists and the limit just from the one side, because we're only talking about the function coming from the one side, from the positive side is the same as f of a. So if that holds, we're fine on the left side, and conversely on this side, this should be b. Let's just change that. We're continuous on the endpoint, on the right endpoint at x equals b if the function value at b is equal to the limit coming from the negative side, the left side. Some other handy theorems of continuity are as follows. If you have a function that's continuous at x equals a, if you've shown that to be true, then you can create new functions through addition, subtraction, multiplication, division, and composition. And that function, that new function, will also be continuous at x equals a. You can just quote this theorem and know that that is true. The only thing you got to watch out for is when you're doing division, that the denominator obviously cannot be 0 at x equals a. Polynomial functions are continuous everywhere. Nice flowing functions, etc., etc. Your previous study of that, you know that that's one of the key properties, and one of the wonderful things about polynomial functions is they flow. They're connected everywhere. Piecewise functions, as we saw in an example a few minutes ago, you need to, in particular, check the continuity at the spot where the domain is split. So in my previous example, x equals 0 was the splitting point for the function. I checked the continuity specifically at that point. There may be other points you need to check as well. Okay, continuity is a concept that comes up in many theorems in calculus, and one of the most fundamental theorems is something called the intermediate value theorem, which says that if f is continuous on a closed interval ab, okay, so I'm going to draw that function between a and b. It's closed, as we discussed. And if c is any value between f of a and f of b, so here's f of a, here's f of b, then there's going to be at least one value of x in the interval such that f of x is equal to c. So we're told that c is between these two y values. We can see that there would have to be at least one, depending on the way the function behaves, there must be at least one value of x that matches up with that value of c. Okay, now again, depending if the function was different, there might be more than that. Let me just change the function. What if the function went like that? Well, then there would be multiple values where x matched up with c. But there must be at least one value, assuming the function is continuous. Okay, a follow-up theorem to the intermediate value theorem is as follows, and this is actually just a special case of the intermediate value theorem, and theorems of that nature we call corollaries. So this function says that if we have a continuous function, and if f of a and f of b have opposite signs, alright, so it's saying one is positive and one is negative. Doesn't really matter which is which, so let me just plug in f of b and f of a. And let's just say the function starts here. It says it's continuous. And here's b. So I have a continuous function on the interval. F of a and f of b have opposite signs. Then it's saying that there's at least one solution to the equation f of x equals 0. In other words, there must be an x-intercept at some point in between, at least one. And you can see that in this case. To conclude, just a simple application of these theorems. We're asked to show that in this equation there's at least one solution between x equals 1 and x equals 2. Alright, so we know that this function f of x is polynomial, and therefore continuous everywhere. We also can calculate f of 1. So if I plug 1 into the function, 1 minus 4 is negative 3, plus 1 is negative 2. And if I plug in x equals 2, I'm going to get 8 minus 8 plus 1. I'm going to get positive 1. And since my output values at these x values are opposite, and since the function is continuous, we therefore know by the corollary we just discussed that there must be at least one value of x. F of something must equal 0. Alright, so let's write our conclusion. Therefore, since f is continuous on the closed interval 1 to 2, and f of 1 and f of 2 have opposite signs, by the corollary to the intermediate value theorem, there must be a value x, at least one, where f of x, which is our cubic as defined above, is equal to 0.